Hello students, this is Professor Chalai, and in this video we're going to look at Hess's Law. As always, you can follow along with our Chapter 5 workbook. By the end of this video, you should be able to define Hess's Law and use Hess's Law to find the enthalpies of various reactions. Let's get started. So earlier in this chapter, we talked about state functions, and I gave the example of a climber trying to climb a mountain, and I said it didn't matter whether the path was direct or he took a different path. A state function simply meant that a state function simply depend on whatever state you were in when you started, whatever state you're in when you ended. Doesn't matter the path you took to get there. So how does this apply to standard enthalpies? Well, remember I said that internal energy is a state function, enthalpy is a state function. So if we have a reaction, let's say reaction A going to reaction B, and we wanted to figure out what is the enthalpy change for this reaction, but we couldn't figure it out. But we knew the enthalpy change for A going to C, going to D, going to E, and then going to B, and we know the standard enthalpies for each of the enthalpy change for each of these reactions. All then we need to do is add them up to get the enthalpy change for the A going to B reaction, because it doesn't matter the path you took to get there, whether it's a direct path or a very convoluted path, you should get the same answer because it's a state function. Similar to the climber, doesn't matter the path. Okay, so let's put that in words. So Hess's law states that if a process or reaction can be written as several stepwise processes. Simply put, that just means that if you have a reaction that could be written as several different steps of reaction, then the enthalpy change, and let's spell that correctly, the enthalpy change of the total reaction equals the enthalpy changes, or equals the sum of enthalpy changes of each individual step. So in the case of this reaction, A going to B, if we couldn't figure that out, we just add up all of the enthalpies for the individual steps, and we should get the total enthalpy for that reaction. Okay, so here's some simple rules when we're dealing with enthalpy changes in reactions. The first says that if a chemical reaction is multiplied by a factor, then the delta H is multiplied by that same factor. What does that mean? Well, let's say we had this, we talked about carbon monoxide in the standard enthalpy of formation being formed from carbon solid plus half an oxygen molecule gas, and this will have a standard enthalpy of a reaction. If we wanted to balance this with whole numbers, then we'll have to put 2 there, 1 oxygen molecule and 2 carbon monoxide gas, and the standard enthalpy for this reaction will be just what it was before multiplied by 2. We multiply every individual mole by 2, and so we just multiply the standard enthalpy of reaction by 2. It's kind of like saying if we go from A to B, right, versus if we go from 2A to 2B. Right, let's say A to B had a standard enthalpy of reaction of 1. Then going from 2A to 2B, we're just adding up 2 different steps of like A plus A to B, which has an enthalpy of 1, plus another A to B, which has another enthalpy of 1. So 2A to 2B should have a standard enthalpy of 2. So if you multiply the equation by a factor, you also multiply the standard enthalpy by that factor. Okay. The second step says that if a reaction is reversed, the second rule, then the delta H changes sign. This sort of makes sense. If we're going from A to B and the reaction, let's say, is exothermic and is positive, endothermic and is positive. If we're doing the opposite, going from B to A, that reaction will be exothermic, and so it'll be negative. So if you're going from A to B versus B to A, if you're reversing the reaction, just change the sign on the delta H. That's what the second rule says. So it doesn't matter the direction of the reaction as long as we keep track of what the direction of the sign is as well. And then finally, the third step says, if a chemical equation can be expressed as a series of steps, then the delta H of the reaction is the sum of the delta H of reactions of individual steps, which is what we talked about here. If a reaction can be written as a series of various steps, then we just need to add up all the various delta H's. So let's see how we can use Hess's law to find a delta H of a reaction. So let's look at number 30. We have a reaction, carbon plus water gas, water vapor, going to give us carbon monoxide and H2 gas, and they want us to find the delta H for that reaction. But the way we're going to find delta H for that reaction is by using these three different other reactions that they give us. So we need to figure out what steps what order and what steps we need, in what order we need to add up these equations on the bottom to get the final reaction on top, and then figure out the delta H from the various different steps. So how do we go about doing that? Well, let's look at the equation that we're trying to solve for, and let's look at each of the different elements. So we see that we have carbon here, and if we look at our various different equations, carbon could only come from this first equation. So we know that that must be one of our steps in our reaction, in our stepwise process. And since we need one carbon on the top, we just need one of these. So we have carbon, solid, plus oxygen gas, going to give us carbon dioxide gas, and the delta H for this reaction is just right there, minus 393.5 kilojoules. Okay, now let's look at water. We're going to make sure we keep water vapor. That water vapor could have only come from this part of the reaction. However, this is in the reactants, in the equation that we're interested in, and in this step, it's in a product, so we need to reverse that equation. So let's reverse that equation. The other thing that we need to pay attention to is we need only 1 mole of water in the reaction that we're interested in, but there are 2 moles here, so we actually need to multiply that by a factor of 1/2 so that we get 1 water. So we'll multiply this by a factor of 1/2, and we'll reverse it. So 1/2 of 2H2O gas, we're reversing the reaction, so we're going this way towards the left, to give us 2H2 gas plus O2 gas. And delta H for this reaction, because we've reversed it, is now going to be positive 483.6 kilojoules. And then I put all of this in parentheses because I know I also have to multiply that by 1/2, because if you multiply the equation by 1/2, you also need to multiply the enthalpy change for the reaction by 1/2. All right. So you might guess the last set of equation that we need to work with is going to be the one in the middle that we didn't look at yet. But let's see how that comes into play. We need to account for the carbon monoxide. The carbon monoxide can only come from this equation. But again, it looks like we need to reverse it. This carbon monoxide is in the product, but in this equation, it's on the reactant side. Secondly, we see we have 2 carbon monoxide in this equation, but we only need 1, so we need to multiply that whole thing by 1/2 as well. So 1/2, we're reversing this reaction, so we start with 2CO2 gas, going to give us 2 carbon monoxide gas plus an oxygen gas. The delta H for this reaction, we've reversed it, is going to be positive 566.0 kilojoules, and I'll put the parentheses because I need to multiply that by 1/2 in the end. Okay, so now we've set this up, let's add them all up to just verify that we actually got the correct equation that we're looking for. So let's add up all the things on the reactant side first, all the substances. So we have carbon, solid, plus oxygen, gas, plus 1/2 of 2 water, so that's 1 H2O gas, plus 1/2 of 2 carbon dioxide, so that's 1 carbon dioxide gas. On the product side, we have a carbon dioxide gas, plus 1/2 of 2 hydrogen gas, so that's 1 hydrogen gas, plus 1/2 of 1 oxygen, so that will be 1/2 an oxygen gas, plus 1/2 of 2 carbon monoxide, so that's just 1 carbon monoxide gas, plus 1/2 of an oxygen gas again, we add that to this other oxygen half that we have, and that'll give us one whole oxygen. Okay, we see that certain things are the same on both sides of the equation. For example, here we have an oxygen gas molecule, and here, so that can cancel out. And here we have a CO2, and here we have CO2, so that cancels out. So what we're left with is carbon plus water, going to give us hydrogen plus CO, which is exactly the equation that we were looking for. So that means that adding up these various steps would work to give us the equation that we're interested in, which means we just need to add up the delta H's now. So here we have negative 393.5 plus half of positive 8483.6 kilojoules plus half of positive 566.0 kilojoules. And so if I add up all of that, my delta H for this reaction will be, if I did my math correctly, positive 131.3 kilojoules. There we go. So that's how we use Hess's law. It's a puzzle, sort of. It's how can we arrange these different equations such that we get the equation that we're interested in, and then once you figure that out, it's just adding up all of delta H's. We have to keep in mind the signs. If you reverse an equation, you change the sign. We have to keep in mind these factors that we placed in front. All right, with that, try numbers 31 and 32 on your own. For number 32, this equation here should be 5H2O. Otherwise, try numbers 31 and 32 by yourself. Pause the video, and when you're done, we're going to go over them together. Okay, let's look at number 31. We need to write the sum of these various equations. So let's look at the first one. We know that we need N2O as one of our reactants, and the only way we can get that is from this reactant right here, but we need half of them because we only need 1 moles. So it's half of 2N2O gas going to give us 2N2 gas plus an O2 gas, and so the delta H for that reaction is negative 163.2 kilojoules. All of that needs to be multiplied by half though. Okay, now we need NO2. NO2 is only found here. Again, we only need half of them though, because we need 1 mole of NO2. So half of, but this is on the reactant side, we need it on the it's on the product side, and we need it on the reactant side, so we need to reverse this equation. So 2NO2 gas going to give 2NO gas plus an oxygen gas. And the delta H for this reaction, since we've reversed it, will be positive 113.1 kilojoules. And all of that needs to be multiplied by a half before we can solve this. All right, and then finally, we're looking for 3 NOs. It can only come from this reaction. Note that we already have half of 2 NOs, which is 1 NO on the product side. So we only need 2 more NOs to make that balance to 3 NOs, right? So we just need to multiply this equation by 1 as it, or write it as is. So this will be N2 gas plus O2 gas to give us 2NO gas, and the delta H for this reaction is just going to be positive 182.6 kilojoules. All right, let's add this all up to see if it makes sense. We have half of 2N2O, so that's just 1N2O gas. We have half of 2NO2, so that's just 1NO2 gas. We have an N2 gas, and we have an O2 gas on the left-hand side. On the right-hand side, we have half of 2N2, so that's just an N2 gas. We have half of an oxygen, so that's half oxygen gas. We have half of 2N2, so that's half of 2NO, so that's just 1NO gas. Half of an oxygen, we add this to the other half of this oxygen to make it 1 full oxygen. And we have an 2NO. So 2NO plus this 1NO gives us the 3NO that we're looking for. Okay, so let's see what things are the same on both sides. We have an oxygen gas there and there, that cancels out. We have an N2 there and there, that cancels out. So we have N2O plus NO2 to give us 3NO, which is the equation that we're looking for. So this all works. So let's just add up the delta H for the reaction. What we have is, let's see, half of negative 163.2 kilojoules plus half of positive 113.1 kilojoules plus positive 182.6 kilojoules. So the delta H for this reaction is, if I did my math right, positive 157.6 kilojoules. It's an endothermic reaction. All right, so I hope that all makes sense and you got the correct answer. If you haven't done number 32 yet, please do so now. Otherwise, I'm going to go over the answer for this one. So let's see. Let's look at this equation. Let's start with carbon. Carbon is only found, where is carbon found? It's only found in this equation. So we should start with that. We need 3 of them. So 3 carbon solid plus oxygen gas to give carbon dioxide gas. The delta H for this reaction is negative 393.3 kilojoules. Make sure we need to multiply everything by 3. All right, next we need 4 hydrogen gas. Where's hydrogen gas in these equations? There's 2 right there, so we need to multiply that whole thing by 2 to get 4 hydrogens. We also have oxygen there to give us 2 water vapor. Delta H for this reaction is negative 483.6 kilojoules, and we need to remember to multiply the whole thing by 2. And then finally, on the right-hand side, we have a C3H8 that could only come from the first equation, but we need to reverse it, right? Because this is on the reactant side, that's on the product side. But we don't need to multiply it by anything, just reverse it. So we start with the products, 3CO2 gas plus 4H2O gas, going to give us C3H8 gas plus 5O2 gas. The delta H for this reaction is positive, because we reversed it, so we need to change the sign, 2043 kilojoules. Okay, so let's add this all up to see what we get. We got 3 carbons, so 3 carbons plus 3 oxygens plus 2 times 2 is 4 hydrogens plus 2 times 1, that's another 2 more oxygens, so this will be 5 oxygens. There we go. 3 carbon dioxides, 3O2 gas plus 4 water, 4H2O gas. All of this goes to give us 3 carbon dioxide, so that's 3CO2. 2 times 2, which is 4 waters, 4H2O gas. A C3H8 gas and 5O2 gas. So let's see what cancels out. Our oxygen cancels out. We have 3 carbon dioxides, 4 water, 4 water. So what we're left with is 3 carbons, 4 hydrogens to form C3H8. And that is the equation we're looking for. So our steps that we wrote down adds up to the correct total reaction. So then we just need to figure out what the enthalpy for this reaction is based off of those steps. So we add up the values for each individual steps. We have 3 times negative 393.3 plus 2 times negative 483.6 plus positive 2043 kilojoules. And I think we add all of those up, I should get minus 104 kilojoules. Okay, so that brings us to the end of Hess's Law. This is a lot of fun to figure out because it's like a little puzzle. Gets your brain working in a very different way than most other math problems. And once you figure out the different steps, you can just calculate the delta H of reaction from that. All right, this brings us to the end of our thermochemistry chapter, which is a very long chapter, and I know a lot of things can seem very similar. We've done the same things over and over again. The reason that we've done that is so that you can get practice doing these sorts of questions. And as always, at the end of every chapter, I include a skills practice question that has even more problems for you to go through. If you have questions, please let me know. If you're working through the practice problems and you see an error or you want to check your answer, please let me know. Otherwise, we'll see you in the next chapter, which goes over a little introduction on quantum chemistry. I'll see you then. Bye.